Good afternoon, everybody. Hopefully you have your packets pulled out, and we're going to go through some of the things on page 8 and page 9 today. So up at the top it says metal reactivity and ionization energy. I am trying to write from my iPad, and the stylus option is a little bit limited, so hopefully you'll be able to read okay what I wrote, and you'll definitely hear it in an auditory fashion as well. So let's go ahead and get started. At the top of page 8, we have two trends we're going to look at today. We started yesterday with metal reactivity. We didn't really get to define it, but we saw some cool demos with lithium, sodium, and potassium. So what we're going to do next is talk about what reactivity is. And what reactivity is basically the tendency to form compounds. So we're going to say give away valence electrons. So the more likely an element is willing to give away its valence electrons, the cooler the reaction we're going to get. And so that's going to tie in with a second trend that we'll look at here in a little bit with ionization energy. And ionization energy is a way to describe how much energy is it going to take to remove the outermost valence electron. So ionization energy is energy required to remove valence electron. And the unit that we're going to measure that in is we're measuring energy. So what you're going to see when we graph and do stuff later, it's going to be kilojoules per mole. So just like we saw joules in physical science for a unit for energy, kilojoules is that same prefix that we would have saw earlier in the chapter that tells you that it takes 1,000 joules to use 1 kilojoule. And per mole is going to be a unit we talk more about as the year goes on, especially in chapter 10. The whole chapter is called the mole. So we'll talk more about moles as things goes on later in the year, but it's a term to help describe a quantity amount. So part A has us doing a couple quick off-ball diagrams here for magnesium, calcium, and aluminum. So I'm going to go ahead and let you fill those in. Okay, we've done a bunch of those together. So I'm going to give you a few seconds here to look over those. You can fill in your arrows for your electrons. The little circles with the P in the end is trying to represent your nucleus for you with some protons and some neutrons in there. And it's asking you, which do you think is going to be more reactive, magnesium, calcium, or aluminum, and why? So you're going to take your guess here, make a prediction. And we already saw the lithium one, the sodium one, and the potassium one yesterday in class. And the sub would have showed you before she started up this video the continuation of that with the brainiacs, with the cesium and the rubidium. So you have an idea of what this trend looks like as you go down a family. The aluminum, the magnesium, and the calcium is to start helping to realize what happens when you go left to right on the periodic table, if you go across a row. So what we're going to notice if we were to do some of these demos with aluminum, magnesium, and calcium is aluminum has hardly any reactivity. If we were looking at it in class in the dish, you wouldn't notice anything going on. You would just see the metal kind of sitting in the little dish with the water. If we were to place the magnesium in water, you wouldn't see things like we saw yesterday with fizzing and bubbling and smoke production. You would see the metal sitting in there, but you would start to notice around the outside edges little itty bitty reactivity. And when we would look at these metals, they'd be more in a powder form than the solid chunks that we saw yesterday. And we'd put a little bit of indicator in there, which is just a clear substance that if a reaction was taking place would change color. And it would change and show us a bright pink color to let us know something was happening. And we would have seen that just around the outside edges of the magnesium. The calcium, in comparison, is very reactive. As soon as we stick it in there, you see the bright pink color show up to tell us the reaction's happening right away. And you'd hear some fizzing and bubbling that you heard and saw yesterday. So you can kind of look back at your prediction with magnesium, calcium, or aluminum and see if you got the correct one right there. But what we have down here at the bottom is answer the following questions in part C. It wants us to do a little bit of comparison. We're going to answer some of the questions, and then we'll come back to the ionization part after we do the graph, because that'll be more helpful. So it wants to know which element, magnesium, calcium, is more reactive. So based on us just talking about the demo, we know that calcium's more reactive, so we're going to circle that. And we'll come back to the ionization energy half of that question after we do the graph. The second one in part C says which element, potassium or calcium, is more reactive. So you got to look at your periodic table and see that potassium is farther to the left than calcium. It's part of the alkali metals, and we saw it yesterday. It was caught on fire and it had a purple flame to it. So we know that potassium is even more reactive than calcium. And just like the previous one, we'll come back to the ionization energy at the end. So the third and the fourth and the fifth questions, we're going to come back to after we make this graph and tie them all together. So let me flip the page here to match yours. And at the top, we can go ahead and do the metal reactivity trend. And then I'm going to have you work on this graph so that we can tie it all together. So we're going to notice that for the metal reactivities, they increase as you go down a group. We saw that with lithium, sodium, potassium, and into the Brainiac video that the reactivity got greater and greater. As you go across the period from left to right, we notice the reactivity drops when comparing sodium to magnesium or calcium. We don't get that same reaction. It starts to die off. And over to aluminum, we wouldn't notice anything happening. So we start to see a big decrease in our metal reactivity. Okay, so let's think a little bit about this part D and constructing our graph with energy. And then we can go back, sum up that trend, and then we can write a reason and a good explanation for both of them. So down here in part D has us looking at creating a graph. And what we're going to do for the graph is on the x-axis, we're going to go ahead and make that our atomic number. And we've got to graph 20 things, so I think just make each line 1, and then you should have room to get 20 of them on there. And then on your y-axis, let's make that ionization energy. Okay, and I think if you did each hash mark as 100, that you could get the smallest data on there and still get the biggest data up towards the top. That would give us a graph going pretty close to 2300, and our big one, helium's at 2372. So we'd be really close in getting that all to fit on there. So what I'm going to ask the sub to do is to go ahead and pause the video and give you about 10 minutes of time to construct your graph. So you're going to go ahead and plot your atomic number and line it up with how much energy it takes. So once you get these all hash marked out, you're going to have all these dots on your graph, and you're going to go ahead and connect them like a line graph so that you can see who the peaks, who are at the top of our graph, and who's at the low points or the valleys to our graph. So if they'd go ahead and pause this video and give you 10 minutes, when the time's up, then go ahead and start it back up and we'll pick back up. All right, guys. Hopefully you have your graph all compiled with all your data points and everything's connected. What we should notice is at the top of our graph, these elements that take a lot of ionization energy, a lot of energy to take their outermost electrons, tend to be our noble gases. You have helium up at the top, you're going to have neon up at the top, and you're going to have argon. And that should make sense because all those electrons and those elements are needed. They're at 8, they have their octet, and they're full and they're stable, so they don't want anybody to take them. So if you're going to take those electrons, it's going to take a lot of energy to get that Zeph, that attraction the nucleus has on them, to break. And then you'll notice your next highest in your table there then starts to be your halogens. You have fluorine and you have chlorine, which makes sense because they just need one more electron and they hit that noble gas configuration. As far as your valleys go, your low points are way on the other side of the table. They're your alkalis. You have lithium, you have sodium, and you have potassium. So what our goal is going to go back to this top of this page and start to fill in an explanation, a reason why for this trend. Okay, so ionization energy, we're going to notice as you go down a group, your lithium, your sodium, potassium, it gets smaller. It's dropping. And the ionization energy as we go across a period from left to right, from lithium all the way over there to neon, increases. It's getting bigger and bigger the closer we are to our noble gases. So let's take these two trends, tie them all together with an explanation, and you're going to notice that it's always about Zeph and size from your Play-Doh and straws that we did yesterday. So the reason for the trend, start with Zeph, okay? You can't just write because Zeph every time. You can start with Zeph, but then explain what it is. So we want to start here with Zeph, and we know that the electrons are farther from the nucleus. Which makes the Zeph